Okay, so picking up at question 10 and working to the end of the paper for the second homework based on the December mark, Unit 1, November 2017. This question is all about rotation. This isn't a topic that's done very well. This does need a lot of practice. When you're rotating a shape, you're turning it 90 degrees anti-clockwise. So on the arms of a clock, we're going to be going against the grain. So we're going to be going this way. And the centre of rotation is at -2, 3. So across to -2, up 3. This is the pinning point. Because I'm working on the iPad, I can't actually show you using the tracing paper, but there's 3 steps to answering this question. Step number 1 will be trace it. So trace that shape onto your tracing paper. Step number 2 will be pin it. Pin it down so that it's held in place at this centre of rotation. And the third step will be to spin it, making sure you're spinning it in the right direction and making sure you spin it the 90 degrees that they're told about. Trace it, pin it and spin it, and on completing those 3 steps you will end up with a triangle over here in line with the first coordinate being -2, 6. And that triangle will be 4 units long, so we'll finish on -6. And it will be there. Trace it, pin it, and spin it. Moving your tracing paper back and forth will be able to check that you've tracked it in the right place. But that anti-clockwise meant that I was going against the clock for 90 degrees. Part B, the question says enlarge, but please be careful, the English language doesn't help us here, because to enlarge a shape by a scale factor of 1/2, it's actually going to shrink. And everything, shrink, thank you. And everything is going to be half the size that it used to be. The centre of enlargement is this point here. So the link between our centre and our corner, our centre, our corner, our centre and our corner will be halved to draw ourselves the new triangle. So at the moment, to get all the way from here at the centre to the top corner of the right angle triangle, I have to go all the way over here to -8 and then down 2, -8, down 2. If I'm halving everything, I'm also halving the distance between that corner and the centre. So I'll only go across to -4, and instead of going down 2, I'll go down 1. So if I go across to -4 and down 1, that's that point there. You should notice it's actually on the grid lines that I drew, and those guidelines, that I drew, and that's a really good sign that it's in the right place. This triangle used to be 1, 2, 3, 4, 5, 6 squares tall. So my new triangle will be half the size, which will be only 3 squares tall. The triangle used to be 4 squares across the base. Now it's going to be half the size, it's only going to be 2 squares across the base, and it's going to be a right angle triangle. And notice all 3 corners of my new half the scale factor, my new right angle triangle, are on those guidelines that I drew before we went any further. Question 11 is from the topic circle theorems. Circle theorems is quite a big topic. There's 7 circle theorems you need to learn if you're going to practice this. I will do a revise with me video to try and cover all of them and to show you some really good questions that are multi-step, involving at least 2 or 3 of the circle theorems, a bit like this one. This is a 5-mark question. To get the 5 marks in this question, you're going to need to know quite a few circle theorems. One of the circle theorems that you need to know is between a tangent and a radius. So here we have tangent meeting radius. We also have on that side tangent meeting radius. And a tangent meets a radius at 90 degrees. So this is a 90-degree corner. Tangent meets radius at 90 degrees, so this is a 90-degree corner. I forgot to say I'm trying to find OQR. OQR is this tiny little angle in here. OQR is just this bit, the red bit. Okay, OQR. So the 90 degrees that I know about is going to be pretty helpful. So that's what I'm going to start by saying. So I'm going to say PQO. PQO, the angle there that I've marked in green, is 90 degrees. And my reason is the circle theorem, angle between tangent and radius. Okay, so the angle between a tangent and radius is 90 degrees. There's also some isosceles triangles going on here. There's two back to back. There's a right angle, an isosceles triangle here, because two tangents meet a chord to make an isosceles triangle. And there is also an isosceles triangle here, because OQ and OR are both a radius. So two radius means two sides of the same length, so it's an isosceles triangle. So I'm also going to colour this little mini corner here in red. Because we've got isosceles triangles, these two sides are the same length, but those two red angles are the same size. These two sides here are the same length, so I'll give them two dashes to show that they are the same size. And I'm going to write that with part of my reasoning underneath. Triangle symbol, triangle PQR, and that's going to be the big one, this one here. So triangle PQR is isosceles, and my reason is lines between a point and a tangent are the same length. So isosceles, lines between chord, I'll put, and tangent, they meet at a point P. So those two tangents are the same length. And I also have those red angles that are the same size because we have the radius OQ and OR. So I've got quite a lot of information there, and I haven't even used the 30 degrees that was given to me here. So if I look to see how that 30 degrees can help me now, I can actually use that 30 degrees with the fact that this is an isosceles triangle, this one, and I can find the size of the angles in these two corners. So if we have a triangle that's 180, so I'm going to talk about angle PQR, this one here. And if I know that I have triangle PQR equals 180 degrees, and then angle PQR, that one corner, would be the 180 degrees, take away the 30, and shared equally between the two, then I actually know they're going to be 75 degrees each. So this one here, 75, this one here, 75. So I got two pieces of angle information in that very corner. I actually have the fact that this part is 75. So this is 75 here, this little bit of pizza. But back at the very beginning, I said that the entire thing was a right angle. So a 90-degree angle if I have all of it. So if I put the red bit and the 75 together, I get a right angle. That pretty much tells me what the red bit must be worth. So angle OQR, the one that they want, must be the difference between the 90-degree right angle and the 75 degrees I just found in the big triangle, which makes only 15 degrees. So these mini angles here must be 15 degrees, so that when you put them together, you've got the full 90. Please note, if they are 15 degrees, this angle here is 150, and that might have been predictable based on the fact that I'm dealing with a kite. But like I said, there's quite a lot of circle theorems, and they're all linked in different ways, and it depends which one you use or which one you spot as to which one you want to actually make sure you're using. Question 12. This is a construction question, and unfortunately I can't do them on the iPad, so you're going to need to ask your teacher. I'll ask Mr. Lloyd to sit down with his pen and paper method and get him to do a few questions on construction and put them all in a Revise With Me video. So keep your eye out for that one. Question 13. Express this number in standard form. The number in standard form is going to start with 4.2. That'll be my choice of number between 1 and 10. You always have to multiply by 10 to a power. If it's a small number like this one, it'll be a negative power. And if I look to see the position that I'd like the decimal point to be in, here, compared to where the decimal point is in the actual number, I can see that I need a 10 to the minus 4. Question B. This is a non-calculator paper, so I'm going to do this using standard form but the long old-fashioned way. Dealing with the whole numbers of 7.2 divided by 2 from this bit, and dealing with the 10 to the power 6 being divided by 10 to the minus 2 for this bit. 7.2 divided by 2, first of all, is 3.6. And with the powers, 10 to the 6 being divided by 10 to the minus 2, you actually subtract them. And when you subtract a 6 and a minus 2, you end up with an 8. So this is going to be 10 to the power of 8. So 6 take away minus 2 gives me 8. So I'll have 10 to the power of 8. This is my final answer, because I had to give my answer in standard form. Question C. This subtraction isn't very straightforward to do in standard form, so this one you're better off writing out the full number. This number starts with a 4 and a 7. And then because of the power 5 here, I know I use one of the powers to leapfrog over the 7, so to speak. So I know that I'll have another 4 zeros. And I'm taking away. This number starts with a 6 and a 2. Power of 4, use up 1, 3 zeros. Now, that's not so straightforward to do in my head. So I'm better off writing it in columns so I can see how the numbers line up. So put the big number on the top. I can see I got 3 zeros, so they line up with the first 3. Then there's the 2, then there's the 6. So 0 take away 0. 0 take away 0. 0 take away 0. But then here, the 0 lines up with the 2. 0 take away 2 won't work. Borrow 1. Give it to the 0 to make 10. 10 take away 2 makes 8. 6 take away 6 is nothing. 4 take away nothing is 4. So I get a number answer of 408,000, 408,000. But the question said to give my answer in standard form. So that's going to be 4.08 times 10. If I run the decimal point in there, that the moment is here. Power of 5. Okay, so the division, I did a quick way by dividing the whole numbers and then sorting out the powers. But the subtraction, I actually had to do it the long-winded way of changing them back into actual numbers before I did the subtraction. Question 14, we've got a Venn diagram, and this long list of bullet points here is going to need to be worked through and checked off in this diagram. Every one of those bullet points, when you read it, will give you a number, but it doesn't mean that that number just gets slotted into one of the spaces in the Venn diagram. It could end up being the total for a circle rather than a number in a circle. A group of pupils from a school took part in the Urdd National Eisteddfod. All of them completed in at least one of the following competitions. So we've got 3 competitions: singing, dancing and reciting. 2 of them only took part in the dancing competition. There's the 2 there. 5 of them only took part in the reciting competition. So I'm going to be putting a 5 in there. They only did reciting. Third bullet point says no one took part in both the reciting and the dancing. So no one took part in the reciting and the dancing. So there's no one in here. Reciting and dancing have an empty intersection. There's no overlap. 3 took part in both singing and dancing competition. 3 took part in the singing and the dancing. There they are. 9 took part in the reciting competition. But the 9 that took part in the reciting competition, I've already got 5 of them in by ear. So I can't just go putting the 9 in. The 9 is actually the total of the entire circle. So that entire circle comes to 9. 5 are already in there. There's only one more space. So those 4 must be in that overlap between singing and reciting. And the last one, 22 there, took part in the singing competition. That again is a total for the entire circle. There's already 7 in that circle. So if that's got to come to a total of 22, there must be 15 in that singing section. And I've used all the numbers in the bullet points, but I haven't, please make sure you put the 9 or the 22 in, because they were totals. They were totals for a circle. They weren't actually going to be in the circle as part of the diagram. Just underneath that then it says, what's the probability that this person only took part in singing? Well, altogether in the diagram there are 29 people, and only took part in the singing was 15. So only took part in the singing would be 15 out of the total in the entire picture of 29. Question 15. This is a quadratic. It gets called a quadratic because the highest power of x is a 2. That square there means that we've got a quadratic equation. Factorize actually means put it into 2 brackets, and then the hence solve means that from those brackets find 2 answers. So I'm looking for a pair of numbers that will multiply to give me minus 18. But I'm looking for the same pair of numbers to add together to give me minus 7. The first thing to start with is the 18. So a pair of numbers that can multiply to give me 18 could be a 6 times a 3, a 2 times a 9, a 1 times an 18. If I'm trying to get them to add to give me 7, it's very likely to be this pair, because 2 and 9 can give me 7 if I make one of them negative. If I make the 9 negative, they actually multiply now to give me minus 18, which is good news. But also minus 9 plus that 2 gives me minus 7, which is exactly what I wanted. So I'm going to have x minus 9 in one bracket and x plus 2 in the other. So that's the factorising part of the question done. But now we've got the hence solve. Hence solve is where or what values of x make this equation worth 0. So what value can I put in there that will make x minus 9 worth 0. That only happens if I put the number 9 in. 9 take away 9. Or, how would I make this bracket 0? What would the value of x need to be there? And minus 2. Minus 2 plus 2 would give you 0. These are called the solutions, and we've now solved it. Question 16 is a pair of simultaneous equations. To work with simultaneous equations, there's a few steps to follow. Following these steps requires you to have matching coefficients for either the x or the y terms, multiplying everything, both left side and right side of the equal sign, to make that happen, and then either adding or subtracting, finding the value and substituting it in. This will take the page. So first of all, I can see here that I have 4x's and 6x's. They don't match. But the first time the 4 times table and the 6 times table come together will be at 12. So if I do this top equation multiplied by 3, that bottom equation multiplied by 2, I'll actually end up with 12x on the top and 12x on the bottom. I'll end up with 12x minus 9y equals 6 on the top, and then I'd end up with 12x, and multiplying by 2 this time, don't forget, minus 10y equals 2 on the bottom. This is called the elimination method, so we have to have matching values here, or in the centre, have to have matching values so that when we combine these two equations now, the x's will be eliminated. So as you can see, the signs here for the 12x's are the same, they're both positive. So if I take them away, one equation take away the other, the 12x take away 12x will actually disappear. It's been eliminated. Then I have minus 9y, minus 9y, minus 10y, minus 9y, minus 10y, which will become an add, and minus 9y plus 10y will leave me with just 1y here in the centre, and 6 take away 2 means that that y is worth 4. So this is my first answer. Y equals 4 can now be put into either of those equations, entirely up to you, so that you can find the x value. I'm going to pick the top one. So here it is written out again as a simple equation. But now that I know this is actually 3 4s, I can change that so that it's a 12. No y's, just a 12. Basic equation, opposite of take away 12 is plus 12. 4x is actually worth 14. Divide by 4 because of the times by 4. 14 divided by 4 is 3.5. So my x answer is 3.5. My y answer is 4. There they are together. Last question on the paper. Quite a horrible looking diagram. A cylinder fits inside a hollow cube with sides of length m. The radius of the cylinder is m over 2. The height of the cylinder is m. The ratio of the volume of the cube to the volume of the cylinder is given by k dot dot m, pi, where k is a number. And we have to find that value of k by working through our information. So to start off with, for the cube, the volume of the cube is going to be the length of the cube times the width times the height, m cubed. The volume of the cylinder is going to be, now think about this, the volume of the cylinder is the area of the circle on the top times the height. So the volume of the cylinder will be the area of the circle, which will be pi r squared. So pi times r squared, which for us will become m over 2 squared. That's the area of the circle on the top, multiplied by the height, which will be m. So this needs to be tidied up a little bit, and that m over 2 that I've got in the bracket to be squared will actually mean that I have pi times m squared over 4 times another m. The m squared and the m can go together, so I can tidy that up one more time and have pi m cubed over 4. That's the neatest version. It tells me to look at the ratio, so that's what I'm going to do. Is I've got both the cylinder and the cube now in terms of m. So here's the cube on the one side, m cubed. Here's the cylinder on the other side, pi m cubed over 4. I can see that m cubed will go into both sides, so it's a little bit like having the ratio 6:8. If I can see that a number goes into both sides, I can divide both sides by that number. For me, it's an m, and actually it's m cubed, and m cubed will go into both sides. So I'm going to divide both sides by m cubed, and that will reduce me to 1, which will give me 1 to pi over 4. And then they're looking for it to just be pi on that side, so I'm going to have to multiply everything by 4, so that the pi isn't a quarter pi, it's just going to be a pi on its own with a 4. So this is my k value, and the last question finishes by saying the k value is actually a 4.